Well, thanks, Wittig and the organizers for the invitation. I have been given the unpleasant task of having to summarize BZSV. Moreover, I think that half of the audience here has already contributed something to the Langlands program, to the relative Langlands program more recently than BZSV. So I'm a little bit uncertain where to pitch the presentation and what to assume. And I also, in my mind, prepared only 2 of the 3 talks in order to give myself freedom to go slower or to present something else tomorrow, which means please feel free to interrupt. Fortunately, afterwards, we are going to have a series of talks on more recent and exciting stuff by J.U. Wang. And also very close to the spirit of this week, which is relative Langlands and arithmetic. You're not going to hear a lot of arithmetic in my talks. So I made it the goal of my presentation to explain one conjecture from BZSV that is not going to be literally used by JU, but is going to inspire the work that he is going to talk about. And this conjecture is 12.8.1, and it says the following. So some assumptions given some assumptions that I will explain later. So these words at some point will be explained. So the conjecture is that the endomorphism ring of the period sheaf localized on a regular locus for the L sheaf is a Clifford algebra associated to the cohomology of the dual symplectic space. Do you want me to explain anything, or is everything clear? Okay, we're done. So this is my goal. So the goal is to explain this conjecture and things relevant to this. So I suppose that everybody here has heard something about periods and L functions and period sheaves and L sheaves. So let me So the relative Langlands program was born not by us, but by people like Piatetki Shapiro, Zagier, Rallis, in order to study the connections between periods and L-functions, periods of automorphic forms and L-functions. Nowadays, we understand
Recording in progress.
Nowadays, we understand periods of automorphic forms in a certain uniform way. So these are integrals of automorphic forms on a group G against theta series. And the integral is over, the automorphic Gaussian space. So throughout brackets G will denote something like adelic modulo rational points of the group G, of a reductive group G. If we're in the geometric setting, we should recall that this modulo, the maximal compact subgroup, is also the stack of G bundles on a curve. So this is also going to have geometric incarnations. So maybe let me take you a little bit back in history. When I was doing my PhD, my advisor, Daniel Bump, wrote, so these kind of constructions are often within what is called the Rankin-Selberg method. And my advisor wrote an expository article on the Rankin-Selberg method, and this included the following description. So typically, a Rankin-Selberg integral involves a group G and a subgroup H, and an Eisenstein series and a cusp form. So three things can happen. First, the cusp form could be on G and the Eisenstein series could be on H. Secondly, the cusp form could be on H, the Eisenstein series could be on G. And thirdly, something more complicated involving unipotent integrations, etc. So let's see some examples where those three things happen. So the first case is when you have a cusp form on G, Eisenstein series on H. So what is an example of this? The usual Rankin-Selberg. So where H is GLN diagonal inside of two copies of GLN. So you consider the integral over GLN of a pair of cusp forms, and then against some Eisenstein series. Another case where this happens, I mean, we don't, or another example is the usual Hecke period. So here, H is just the multiplicative group inside of G, which is GL2. And of course, Eisenstein series on H is just a constant function or a character. So you consider the integral of a cusp form against a character of the multiplicative group. Examples where you had an Eisenstein series on G and a cusp form on H. Include, first of all, examples. First of all, they include the doubling method. Where you embed the group H into a larger group. So let's say that H is a classical group like SP2N, and you embed it inside G is equal to SP4N, and then you take an Eisenstein series here. Or another example is the Garrett triple product L-function, where you take H to be the product of GL2, 3 copies of GL2 with the same determinant, and you embed this into GSP6, and then you take an Eisenstein series here, and you integrate it against 3 cusp forms, and that gives you the triple product L function. And thirdly, there are cases of the Rankin-Selberg method which are more complicated. Well, that's not a very precise description, but for example, they involve unipotent integration. And one example here is the generalization of the Hecke periods to GLN. So generalization of Hecke to GLN, where you take an integral of this form. So you do have a multiplicative group here. So this is going to be a mixture between the Hecke period and the Whittaker period. So for the rest of the group, you take a Whittaker period. So you have some entries here. So, and here you have x23, x34, and so on and so forth. And besides the multiplicative character, you also added an additive character. And of course, we nowadays have the beautiful big framework of the Gann-Gross-Prasad conjectures. So many of the GDP periods interpolate between, so I don't need to write anything, but many of the Gann-Gross-Prasad periods interpolate between the Whittaker period and other periods like the orthogonal Gross-Prasad period. So this was the landscape on the automorphic or period side, and all of these integrals are related to certain L functions. But we want to see all of these different examples as incarnations of the same thing. And theta series are a way to do that. By the way, to make things worse, the pioneers of these methods, including Bump, Ginsburg, also had many, so they also had many Rankin-Selberg integrals that involved theta series coming from the veil, from some oscillator, some veil representation. So all of this jungle of the of integrals we're going to call period integrals. So how to think about them in a more systematic way? Which one is number one now? This is number one, I think. So these are all, this can be viewed uniformly as theta series. And here for a few minutes I'm going to make some trivial observations. Really there's nothing really sophisticated in what I'm going to say. So suppose that H is a subgroup of G. So we can consider the integral over H as a distribution on the automorphic quotient space for G. And you know, any automorphic form in an automorphic representation on G can be written as a finite sum of convolutions F equals Hi convolve with Fi, where Fi's are also in pi, and the Hi's are compactly supported smooth functions on G, or even you can take them to be Schwarz functions on G. That the difference is only at the Archimedean places. So every form can be written like that. In the p-adic case, this is obvious. In the Archimedean case, this is a consequence of the theorem of Dixmia and Mayaven. So that means that if I pair this with the integral over H, so if I write integral over H, comma F, I'm thinking of it as a distribution, so a pairing, this is the same as integral over H sum Hi Fi, and you can bring the convolution to the other side. So this is going to be sum over I Hi dual convolve with the integral Fi, where Hi dual of G is simply Hi G inverse bar. By the way, are these boards equivalent, or is there any reason I should or shouldn't use them? I can use all of them. Okay. So now setting phi of x equals integral over the adelic points of H of Hi gx dg, Hi dual gx dg. So this is now a Schwarz function on G mod H. And let's call G mod H, let's call it X. This is a G space. And what we have here, so we have this distribution, but we're convolving it with a smooth function. So this gives a smooth function on the automorphic space of G. And this happens to be the same as the theta series of phi I. What is the theta series? The theta series is a map from Schwarz functions on x of a to automorphic functions, which is simply by summing phi goes to the function which sends g to the summation over the rational points here of gamma g. So, okay, in practice you can have analytical difficulties depending what f is. This integral may not converge and so on and so forth. But in any case, at least when x is quasi-affine, x of f is discrete in x of the Adels, and the theta series is well defined by convergent sum. So, long story short, so I explained, this explains to you how the integral, this explains, hence, now the pairing with this singular distribution can be written as sum over I, integral now, so the pairing between theta series phi. So you can view this as a pairing of a space that doesn't know anything about automorphic forms, just adelic points of a G variety with our automorphic representation. And all the integrals that I presented on the board can be reformulated in this language. So in the end, all we care about is to integrate automorphic forms against theta series. Okay, and I think I don't need to give more details, but all the integrals that I wrote there can be reformulated in this language. Okay, with a slight modification, when you see these unipotent characters, instead of starting with Schwarz functions, you need to start with some other sheaf of functions. For example, Whittaker functions. Okay, Whittaker functions are not functions on G mod the unipotent. They are functions on G that vary by a character of the unipotent. But modulo this small generalization, everything that I have written there on the board can be understood this way. Moreover, you can also use this. So here x was G mod H. So this was a G space, but there is a slight generalization in order to include the theta series coming from the veil representation. So, well, first, the first thing I'm going to say is not strictly a generalization. So let M be a symplectic G representation. Then to this you can associate the veil representation of the metaplectic group, which is a cover of the symplectic group of M. And here I mean which is a cover of, here I mean the adelic points, the cover of the adelic points of the symplectic group. And there is a theta series construction to functions on the metaplectic group, automorphic functions on the metaplectic group, which by restriction you can restrict to your favorite group, modulo the fact that you have to, in general, you have to go to the cover, to the metaplectic cover. And this theta series construction looks the same. So if M is written as a direct sum of Lagrangian subspaces, then the Schrödinger model realizes, well, here I really mean the smooth vectors of the Weil representation, so realizes the Weil representation as Schwarz functions on X of A, and then the theta series is, well, then again you can sum over the rational points. That gives you a functional, and it turns out that this functional is automorphic, meaning it is G of F invariant. This is not a priori obvious because this Lagrangian is not necessarily G stable. So this functional is GF invariant, but this is part of the theory, of the global theory of the Weil representation. So it's not obvious because G doesn't necessarily act on X. Okay? So I will be using the word polarizable when G is acting on X. When G is not acting on X, we're going to be talking about non-polarizable. This is a reference not to the space X itself, but for example, the symplectic space. So the basic object, the basic input in the current versions of the relative Langlands is a pair G comma M, where G is reductive and M is a Hamiltonian, so symplectic variety with a moment map. And polarizable means that M is the cotangent space of a G space, or some twist thereof by a character. I'm not going to talk about it yet. Okay, so like I said, I expect that the audience is completely bored by now, and I don't want to lose sight of the main target, which is to explain this conjecture that I have written there. So, staying on the period side, and without offering any specifics which you may or may not have seen. Yeah, I want to talk about period shifts, but maybe as an interlude, let me talk about something which is called the anomaly, since I just mentioned it. So the word anomaly is used, it came from somewhere in physics, but it's used to say that here you really need to work with metaplectic groups. So still in the setting where G maps to the symplectic group of some vector space, symplectic vector space, we say that this is anomalous if the metaplectic cover does not split over G. So anomaly means that the metaplectic cover doesn't split over the adelic points of G. So this is there's a combinatorial condition that can detect anomaly. So I don't know if it's worth mentioning it, so it's very fast, so let me say. So anomaly means that if you take the weights of this representation with multiplicity, mod plus minus 1, so this is a symplectic representation, so these are the weights of M. You restrict M to a maximal torus of G, so at least, this is at least when G is split. So you take the weights of the symplectic representation. These appear in pairs, of course, because it's self-dual, so you can multiply. So you only take one representative, and you sum this. And the question is whether this, up to characters of the group, has a square root. So the anomaly is equivalent to saying that this does not have a square root up to characters of the group, which are the Weyl invariants of the character group. Okay, so this is something, I wrote it down just to convince you that this is something that's not so hard to check. And BZSV assumes the varieties to be anomaly free, but I want to emphasize that this was partly for convenience and partly because of our relative ignorance of the metaplectic case. In general, we make a lot of assumptions in BZSV that simplify the situation. That doesn't mean that these are the interesting cases to consider. In fact, the most interesting cases to consider are beyond what we have already sort of understood. So there is no reason why you should restrict yourself to this, but for convenience, we restrict ourselves to this, which means that all the theta series that I mentioned before are actually on the group G itself and not a metaplectic cover. Okay? But one interesting observation, experimental fact that we have not explained yet because this theory is still largely conjectural, is that this condition of being anomaly free seems to be preserved by relative Langlands duality. So relative Langlands duality claims that for nice spaces, for nice pairs GM, there's also a corresponding pair for the dual group. And the experimental observation is that anomaly freeness is preserved under this, this duality. So nice here in BZSV has the name hyperspherical. Yes. Well, sorry. It's true that if what am I saying? No, yeah. Yeah, because the other case is Fourier-Jacobi. Yeah. Okay. Sorry?
Do you believe that non-hyperspherical varieties should have a dual? No.
Great. So we're going to get to these questions if I manage to wrap up today what I want to say, because these are the questions beyond BZSV. So I can say something about that. So I'll make sure to say, but not right now. So the question was whether non-hyperspherical variety should have a dual, and I think the answer is yes, but I don't want to, it's very tempting to start speculating, and I don't want to do it just yet. So, okay, so now long story short, suppose that you have a pair G comma M, where if you're not very familiar with the story, you should really think about the polarized case, where X is a G space. And then we have already seen the theta series, which now we will also start calling period function. So it's not a unique function, of course. The theta series, we said, is a map from x adels to C infinity G. Yeah, actually, let me not call it period function. So the geometrization of this, so there's a geometric counterpart when f is a function field. So f is the function field of some curve sigma. So sigma is a smooth projective curve over fq. But I will only describe, and we only describe this geometric counterpart in the totally unramified setting. Not that you couldn't do it beyond that setting, but let's start from the totally unramified setting. So in the totally unramified setting, you have the benefit that you have a, by the way, X is assumed to be smooth. Quasi-affine. So in the totally unramified setting, you have the benefit that you have distinguished unramified functions. So you have the characteristic function of X of O. These are the completions at all points of the local rings. So this is a distinguished unramified function on X, and its theta series is going to be called the period function. X is, excuse me? Well, everything is over FQ, yeah. So just for simplicity, you can also take let it vary over the curve so G X over FQ, just for simplicity. So this is going to be the period function, and this geometrizes to the period sheaf curly px in well, let me use this vague and confusing notation sheaves on band G before I remind you a little bit the relations. What does it mean that it geometrizes? It means that if you take a Frobenius trace, you get from the sheaf to the function. Okay, so now quick recap of this relation between sheaves and functions. So well, I'm going to use the word recall, which means that I recall that in this setting, if I take the automorphic quotient of G, so GA mod GF mod the maximal compact subgroup, this is the same as FQ points of the stack of principal G bundles on the curve. So, so for example, when G is GM, what do I have on the left-hand side? On the left-hand side, we have E dels mod F star mod the units. But this quotient here is divisors on the curve. Sorry, the curve was called sigma. This is divisors on the curve. So these are divisors modulo principal divisors. So this is the Picard group of line bundles. Okay, so these are line bundles defined over FQ. Now, what do we mean by sheaves? It's this usual ambiguity in the geometric Langlands program. Sheaves can mean anything that's of constructible nature. So whenever we put sheaves, we mean some constructible category, some type of derived category of sheaves of constructible nature. In other words, I'm not talking about quasi-coherent sheaves here. I'm talking about something like étale sheaves, or if you want to think about these things as Riemann surfaces and moduli space of G bundles on the Riemann surface. You can think about these things as D modules. Sorry, the Riemann surface comment was. So you can think about these things as D modules. Yeah, so there are variants of this, but in any case, if you want to translate between geometry and functions, you need to take some trace of Frobenius somewhere, so you have to work in the étale category. Okay, so let me not get into this anymore. Actually, sorry, I said something. I jumped ahead in these distinctions between sheaves. So, yeah. So maybe let's stick to the. Yeah. No, it's fine. It's fine. So okay. So what is the period sheaf? Over the modular space of G bundles, so this is associated to a G space X. Over the moduli space of G bundles, you can define a moduli space of G bundles with an X section. I'm going to get to it in a moment. And then you have the projection map here, and you define the period sheaf to be the projection of the constant sheaf upstairs. By the way, K is our field of coefficients. Which we will take to be of characteristic 0 and algebraically closed. Now, what does band Gx parameterize? Band Gx parameterizes pairs, curly G and sigma, where curly G is a principal G bundle on the curve. So here, of course, we have to take the curve over the algebraic closure, over everything, all the geometric constructions are over FQ bar. And sigma, so if you have a principal G bundle, what does a principal G bundle look like? I have the geometric curve sigma, which is something like a Riemann surface. A principal G bundle has fibers which are principal G spaces. They're isomorphic to G up to translation. So G acts simply transitively on them. So now if I have a G space X, I can use the G bundle to twist the space. I can take the product with this and then divide by the simultaneous action of G. So this gives me a twisted version of the space X. So this gives me a twisted version of the space X, and a principal G bundle on sigma induces an X bundle, so to speak, by this construction, and then sigma is going to be a section of this associated X bundle. So let me give you an example. I talked before about the Picard group. The Picard group classifies line bundles, but line bundles and GL1 bundles are not literally the same, right? So a GL1 bundle corresponds to a line bundle by removing the zero section of the line bundle. So this is the kind of construction here. So if G is a GM bundle and X is A1 under the action of GM, then what I denoted here by curly X is the principal, is the corresponding line bundle. Okay. Okay. And then what is Ban XG in that case? Well, this is something familiar to anyone who has seen, something about the Picard group as a variety or as a stack. Non-zero sections of the line bundle correspond to divisors. So this here is going to be the scheme of divisors union the zero section. So what are divisors? Divisors are given by the symmetric powers of the curve. Okay? But these are the non-zero sections, and then you have the zero section, which can be identified with the Picard stack. So this corresponds to the zero section. Of course, the union is not disjoint. There's something, there's some interesting geometry, some interesting gluing here. But this is not a very mysterious space. So claim suppose that everything is defined over FQ. As I already said in the beginning, but then I told you that all these bungees and all of these things are about the curve over FQ bar. But suppose that everything is defined over FQ, my curve, my group, okay, then these sheaves have an action of Frobenius. And at the fixed points of Bun-G, so the FQ points of Bun-G, I can take trace of Frobenius on the stocks. So I have a sheaf function dictionary So sheaf function dictionary from sheaves on Bun-G with a veil structure. So that's the action of Frobenius that will come automatically for my constructions. Two functions on Bun-G FQ, which we already said are automorphic functions, unramified automorphic functions. Okay, and the claim is then that the image of the period sheaf is the theta series associated to the distinguished Schwarz function. So it's the period function. Again, as an example, in the same example, so let's see. Again, so I'll take X to be A1 with the action of GM. So what did we define our period shift to be? Our period shift, we define it to be the push forward of the constant shift. So if you take now a point in the Picard group, so trace of Frobenius on the stalk of this is going to count number of points on the fiber, right? The fiber is the space of sections of this line bundle. So this is the function. So by construction, trace of Frobenius on this period shift is the function that takes a line bundle L in the Picard group to the number of sections of the line bundle over the curve. So let's compare it with the period function. So the period function, so the line bundle here corresponds to the class of any del of G, an adelic class of G. And it corresponds in the way that we said. G gives you a divisor, so that's the corresponding line bundle, okay? And what does the period function at G evaluate to? Well, this is the sum over gamma in F, so over rational functions of the characteristic function of O hat, because that's the function we use to build the period function, gamma G. So when you present line bundles by divisors, these are really the rational sections of the line bundle. And here you're counting how many sections are, so here you're only allowing the sections that are regular, right? So gamma, you think of F as the rational sections of the line bundle, and you think of those as the regular. So to land in O hat at every place means that the section is regular. And maybe, I mean, I'm secretly inverting G here, so the way I'm associating G to a divisor requires some inversion, but this is just the sum of the constant function 1 over actual sections of the line bundle. So rational sections that are regular. So it is the same function. Final thing that I want to say about period shifts and period functions. Are there any questions? Yes.
So I guess in this case, we are thinking of M as T star X, right?
Yes.
In a non-polarizable case.
Final thing I want to say. is that, so all of this was in the polarizable case. So the non-polarizable case, well, in the non-polarizable case, it turns out that, so we've seen already that we can make sense of the period function px. Well, there is no x really here, right? We think about the cotangent space of x, but we've seen that we can make sense of the period function px using the Weil representation. And similarly, this has been done by Lysenko. You can make sense of the period sheaf using a geometric version of the Weil representation. So there is a way to do Weil representation with sheaves, and that doesn't present a problem to defining the period sheaf in that case. Did I answer your question? Yes. Yeah, okay, so this is a little bit, so in general, so here, by the way, so my notation here is problematic because there's no G space X, right? So maybe we should start with a Hamiltonian space M. Now, I explained two cases. I explained the polarized case, and I explained the vector space case, the case where it's a symplectic vector space. The general case would be a combination of those two, and there's no problem in combining the methods.
When you say general, you again mean hyperspherical, right?
I mean against hyperspherical general for now. All right. Now, on the other side of the correspondence, we should have L functions and L sheaves. So what's the geometric version of the L function? So recall that, okay, so again, we're going to take f to be the function field of a curve. And of course, the Galois group of this includes many ramified extensions, but at least the unramified Galois group can be thought of as an étale fundamental group. And I'm going to suppress base points. I apologize if I hurt some sensitivities. So there is the étale fundamental group of the curve over FQ. And of course, an obvious unramified extension you can do is go from FQ to FQ bar. So there is this short exact sequence. Let's call this just pi 1. So where this is the fundamental, the geometric fundamental group. So this is the étale fundamental group of the curve over FQ bar. We are going to be working with Langlands parameters, understood here as Galois, just simply Galois representations, or you can use a veiled version, but let's not worry about this yet. So if you have a Langlands parameter, so an unramified Langlands parameter, you can you get a geometric, so Langlands parameter into what? So phi goes from pi 1 to some L group. So the geometric Langlands parameter is simply phi restricted to pi 1 geometric. So this is going to be to go from pi 1 geometric to, I don't need to write L group here, I can just write the Langlands dual group. So this we will think of as a G-check local system. Yeah, so I say we will think of it as a G-check local system because, again, the word local system depends on which setting you're working on. You're working on the de Rham setting, you're working in the étale setting. You can even work in the Betti setting where you think of the curve as a Riemann surface and you just talk about representations of the usual fundamental group. Okay, so this here, by the way I presented it, is étale. It's an étale local system. Okay.
Should correspond to some SL2 with the tangent SL2 or not SL2.
Why does Frobenius correspond to an SL2?
No, never mind.
Yeah, so let me remind how the L function is geometrized. But yeah, maybe, yeah. So so for example, for example, if this group is GLN, then what does this representation capture? It captures the monodromy of the local system. Fix a fiber, which is your base point, and then go around, and then you have a monodromy representation, right? Okay, so there are too many options with the boards. I kept. It's like walking into a French wine store. I have another 10 or so. Okay. So forget about G and G-check now. Let V be a linear. So it's not a G-check local system, it's just a linear, a usual local system on the curve. So again, étale local system on the curve. So that means it corresponds to a Langlands parameter where this is the fiber at the base point. So then we can define the L function, and the L function of V, of phi, evaluated, let's say, at 0, has the following form, that it is the, well, product. So you can express it in terms of the cohomology of the geometric local system. So I from 0 to 2, because that's where you have cohomology. And then I have to take determinant of Frobenius acting on cohomology, but a nicer way to write this is as alternating trace of Frobenius acting on the cohomology of the geometric local system raised to the power -1 to the I plus 1. So what this tells you here is you have a fraction where in the numerator you have h1, in the denominator you have h0 and h2, and you're calculating, first you're calculating something completely geometric and topological. You're calculating the just the cohomology of this local system. But then, because everything was defined over FQ, this comes with an action of Frobenius, and you take the trace of geometric Frobenius on this. Okay? No, there is no reason why I wrote underlying trace. I'll explain in a moment. Okay? Sorry, I said it and I didn't write it. So this is a determinant, so I should put, yeah, so that's why I wrote alternating trace. So this is the exterior powers of H, right? So I want to write down the determinant, and underlying trace means graded trace. Okay, so on odd powers I get, all right. In fact, there's another, a more graded, a nicer graded way to see this. So instead of, so it uses this nice formula which some of you may have seen. And instead of factorizing the characteristic polynomial like this in the denominator, you can write the corresponding series in the eigenvalues, but that corresponds to changing the exterior powers, to replacing the exterior powers in the denominator to symmetric powers in the numerator. Okay? Also, in some sense, the exterior power in the numerator is an exterior power of H1. So in the graded sense, it's a symmetric power. So a nicer way to write this is as graded trace on graded symmetric powers of the whole cohomology. And you just have to keep track of how you define the gradings. Okay? Again, these are graded. So on an odd vector space, symmetric means exterior. And I forgot the Frobenius somewhere along the way. But now, what is symmetric powers of a vector space? Symmetric powers of a vector space is functions on the dual vector space. Right? So symmetric powers of a vector space is functions on the dual vector space. Okay, so here we said graded symmetric, so we need to think about the dual vector space as a dual vector space, and we need to think of functions in some derived algebra geometric sense, where if you have a vector space in odd degree, then functions on the vector space is not the symmetric power of the dual, but the exterior power of the dual. But up to these conventions, this here is the coordinate ring, the derived coordinate ring of the dual graded vector space to cohomology. But what is dual to V? By Poincaré duality, dual to this vector space is the cohomology of the dual vector bundle. So what I wrote here as dual graded vector space to the cohomology, this is simply the cohomology of the dual vector bundle. And if you are, if you are an arithmetic person, which you should be because it's in the title of the conference and also because we're taking Frobenius traces, the dual needs some kind of Tate twist. So, in other words, we're viewing the cohomology as some variety in some derived world, and we're taking functions on that variety and trace of Frobenius on those functions. So what is this variety? Well, you should think about H0. H0 are just the sections of the line bundle, of the vector bundle. So more generally, the cohomology in the derived world are derived sections of the vector bundle. So there is a derived scheme. So fact a derived scheme which I will call, well, sections of the dual vector bundle. Forget let's not worry about Frobenius now. So there is a derived scheme, sections of the dual vector bundle, whose functions, well, the function should be a Digi ring. This is somehow the cohomology of the Digi ring. So whose functions, after taking cohomology, so the functions are going to be some complex, but the cohomology of the complex will be this graded symmetric power of the cohomology of V. So this is what, so maybe I don't have more time, so let me stop here. In the late evening, if you're not completely drunk, you can come back and we'll talk about how we use this, how we generalize this to define L-sheaves, and then hopefully by the end of the evening I will have said something about this conjecture that's related to the talks of Zagier. Okay, let's stop here.